Test, 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 test. Test, 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 test. Hello, Beck. All right. got our speaker, my name is Prof, and I'm the chair of the Geological Sciences Department. Welcome all of you. About yeah. So. He went out and worked for a major oil company, and they were so impressed with him that they themselves donated funds, bringing the lecture once a year to our department at the university. That's pretty neat. You have a job alma mater to help them out. So we appreciate that. Our whole department thrives on the support of our alumni. Is this working? Yeah, okay, this is good. Great, thanks. So our students are blessed by not just for scholarships and all, but many of our students work in what's called a mentored environment where they get the opportunity to work one-on-one with the professor on research, and that's largely funded by external donations as well. But tonight we'll start off here with an opening prayer, and it's going to be offered by Dr. Josh Lamont.
Our Father in heaven, we are grateful this evening that we can join together for this lecture. We're grateful for Dr. Bickmore and his scholarship and his leadership and his example as a disciple scholar. We're grateful for the opportunity to be associated with this university and for the opportunities that we have here to study and grow our faith as we study and learn of thy creation. We're grateful for thy Son and his example and strive that we will strive to be more like him. And we pray that as we go through this lecture tonight, that we will be attentive, that we will allow the Spirit to be with us, and we will leave here in safety. We say these things in the name of Jesus Christ. Amen.
Thanks, Dr. Lamont. So Dr. Bickmore is going to be talking tonight about science as storytelling. And I got to tell you, the first time I saw that paper, it's part of a paper he published, it just grated on me. I didn't like it that much. And then I used it in class, and it changed the way I taught, not just about science, but also about the way the interface of science and religion. So it really makes a big difference. So I'm going to read you a little bio about him. He's been teaching here for, 23 years? And he teaches mineralogy and geochemistry. You work on dinosaurs at all? No, okay. And science education. It really makes a big difference. And right here at BYU with a bachelor's in geology. He then earned a PhD in geochemistry at Virginia Tech. While he's still an undergraduate at BYU, he met his wonderful wife, Keiko, and they now have a son, a son-in-law, 2 daughters, one right here, Autumn, a daughter-in-law, a granddaughter, and 2 granddaughters on the way. That's great. Here's the most interesting thing about him. He can also make his tongue look like a snail, but he only shows it to small children. You're all out of luck tonight. So now with that, we'll turn the time over to Dr. Bickmore.
Okay, so is my mic working? Go like this if it's working. Okay. All right. So obviously from the title of the presentation, You can probably guess that the primary audience I have in mind for this is people who teach science, right? But in fact, I really mean it for a wider audience, for people, anyone who, I guess, who has to talk about science with other people, which nowadays means anyone who gets sucked into political arguments on Facebook or social media. It'll come up. Okay, what I'm trying to do is show how to take a science teacher of any background. They could be religious, they could not be religious, they could be this kind of religious, they could be that kind of religious, doesn't matter. So any background with a class full of students of any background, and rapidly create an environment where the students develop a more sophisticated understanding of what science is about and how science works, and they feel more free to explore scientific ideas that may seem problematic given their religious or ideological backgrounds. Okay, so I'm including, political persuasions and anything like that. Okay, so this is sort of an outline of what how I'm gonna proceed, but not exactly, because I'm gonna be going back and forth with the last two. Okay, so I'm going to talk about what the problem is that we're trying to solve. I'm going to talk about a particular type of solution that everyone seems to promote for solving this problem in science classes. And I'm going to talk about how, I actually agree with a lot of that, the solution that everyone sells, right? But I'm going to talk about how you can run into some mines when you try and put that into practice. I'm going to try and show you where the mines are and give you a way to navigate around all those mines. And the point of this also is you can be teaching science and think you're doing a great job, because most of the students are responding just fine to how you present some of the things. But often there are other students in there that are not having such a great time, and there are things you can do to reach them too, okay? So we're trying to broaden your reach as far as who you're getting to in your class. So the first part of the problem is baggage, okay? When a student comes into a class, they're not a blank slate. They come in with all sorts of prior ideas, That could include, misconceptions they come in about the subject matter. It could be, like I had mentioned before, religious or ideological conflicts with the subject matter. And also, it could be mistaken or oversimplified ideas about what science is or what it should be. And we make this problem worse if we fail to confront this directly. Because studies have shown that when students who have some kind of hang up about what the subject matter of the class is, come into class, they're not, for the most part at least, they're not constantly raising their hand and challenging the teacher so that you know that they're having a problem with it. Instead, they usually just check out. They do the bare minimum that they have to do to get their C and get out of that class. And it has very little impact on them. So let's talk about something else here. This is just showing you the broad range of baggage that can come into your class, right? So this was something my wife, Keiko, this is her 17 years ago or so. She told my daughter, Autumn, who's here tonight, some people are afraid of science. They're afraid they won't be able to understand it. They're afraid to try it and find what is interesting about it. And she said, yeah, but more people are afraid of being eaten because being eaten is not fun. So, and now she's an actress. So there's all kinds of students. We want to reach all of them, okay? Okay, so the solution that everyone says is the way to go is to teach students more about the nature of science. What is science? What is it supposed to be? How does it actually work in practice? Okay. And so, for instance, I'm showing you the cover of a book put out by the National Academy of Sciences. So, very reputable organization, right? Called Teaching About Evolution and the Nature of Science. Now, my presentation isn't just about teaching evolution. There's a lot of things that come up if you teach anything about climate change or cosmology, or there's any number of things that aren't just about this, but this is the thing that has been written about the most, I guess. Okay, so it's going to come up as an example of what we're talking about more than once. Okay, so in a book like this, what are they wanting you to say to the students about the nature of science? Well, what they say is that there's sort of three main aspects of it that the students need to understand. Number one, it's empirical, which just means it's based on observation, which is something that everybody already knew about science, right? But also, we have these other aspects of it. So there's a tentative nature of science. So for instance, here's a quotation from that book that I'm showing here. The statements of science should never be accepted as final truth. It's just a tentative conclusion. All right, so also, it's creative. So here's a quote I have by Albert Einstein and Leopold Infeld. And they say that scientific explanations are free creations of the human mind and are not, however it may seem, uniquely determined by the external world. In other words, we make this stuff up. We make up explanations. And it's always possible that there could be another explanation that we haven't thought of that could be even better or closer to the actual truth. Okay, but it's a creative process. Whoops. Okay. So here's the first mine that you hit. If you're trying to teach that to students, and that is they think they already know what science is all about. Why? Because they had that lesson in junior high science about the scientific method. So they think they know. And what they think they know is usually this. Science is empirical, which is true, right? But they think that's it. In other words, they think science is just the facts. That's what it's supposed to be anyway. But what they also actually do know is, you can avoid this if you watch TV news or anything like that, is that sometimes science and scientists can be wrong about stuff. Okay, so how do they put that together if they think science is supposed to be just the facts, but in fact, science is sometimes wrong? Well, the way that typically goes is that they divide science into two categories. Well, there's the good science, which is just the facts, and people doing it right and come up with solid conclusions. And then there's junk science, which is any science that has any gaps or gray areas or oversimplifications, et cetera, okay? Which, in fact, is all of science. If they really knew what science was like, they would put it all in that junk science category. But they think that there's this other kind of science where it's all just the facts. And so the upshot of this is, what happens is that when they're confronted with some theory or conclusion of science that they don't like because it's inconvenient for whatever, ideology that they, or baggage that they are carrying in, they can just, go into it deep enough to find any gray areas or anomalies or whatever, and then dismiss whatever they don't like. But what about all the good science? Wouldn't they find the same thing with the good science? No, because they don't pay that much attention to it, right? If they don't have any reason to disbelieve it, most people will just not look into it that deeply. And so they can keep this illusion up in their mind, but still have an excuse to dismiss without really taking into account the evidence or looking into the evidence at all, whatever they want. Okay, so how do we get around that? That mind. Well, one way to approach it is through guided by what is called conceptual change theory. So it's a pretty well-developed educational theory. And it's very simple. The idea is that students come into class with misconceptions. Obviously, they all have some. And if you don't confront those misconceptions directly, what happens is that they'll be listening. Yeah, that makes sense. They think they kind of know what you're talking about, so they're not paying very close attention. And so they take the new stuff you're saying and sort of paste it onto the surface of their brain and don't think about how what you're saying actually contradicts some aspects of what they already thought. And so therefore, after a couple weeks or months or whatever, all that new stuff just sloughs off and you're left with the same old misconception again. There's a lot of studies showing this is what basically happens if you're not very careful about confronting their misconceptions. So how do you confront the misconception? I have here a picture of a baseball bat to symbolize that you really have to hit people over the head with it and let them really confront the fact that what you are saying is not the exact same thing that they already think they learned, okay? So you can do that in a few ways. One way would be just to have them perform experiments that specifically address their misconception. That can be sort of a jarring experience that will get them in the right frame of mind. Another way is to use a refutational text, they call it, meaning give them a reading assignment and make them engage with it, which explicitly talks about their misconception and why it's not exactly right and so on, okay? So you hit them over the head with that and then give an explanation of what you want them to understand in exceptionally plain and simple language, okay? And if you can pull that off, then they can move toward better understanding. All right, so obviously we developed this science as storytelling program in order to accomplish that, but it's centered around this essay we wrote, and we have here where it's published and a URL or and a QR code if you want to download it or whatever. You can get it there. But anyway, before we get into the content here, let's first look at the title. The first thing they see is the title, and it says Science as Storytelling. That is our first bat, right? Do people usually think of science that way as a sort of a genre of storytelling? No, they don't, right? They think of it as just the facts. And so right off the bat, that is, so the bat, that was not intentional, but I'm keeping it. Okay, so right off the bat, that gives the impression that we're talking about something that isn't set in stone and it's creative, right? Just from the title. Now, when I try and pitch this program to other scientists, like Brooks said when he was up here introducing me, the biggest pushback I get is they'll read it and say, oh, well, everything you said was true, but I hate that word. Hate it. Why? Because they feel like it's going to make students think of science as less than it is, right? It sounds too fictional, right? They don't want to really get that across. But point one, that's our bat. And if you don't use the bat, find another one, right? You have to do something to draw attention to the fact that what they thought about science, and they got, like even what they taught them in junior high is probably more sophisticated than what they actually got out of it, right? So what they think they know is not what you are trying to talk about. Okay, so now the first point about this is that, hey, I already gave you the quote from Albert Einstein and the other guy about scientific explanations being free creations of the human mind, right? That's pretty out there. But here's another guy. This is Peter Medawar. He won the Nobel Prize in Medicine in 1960. He said in one of his books, scientists are building explanatory structures, telling stories which are scrupulously tested to see if they are stories about real life. Okay, so this, you talking about storytelling in the context of science is not a new thing. It's a really old thing, okay? And some really good scientists have been using that language in order to try to get across the idea that science is tentative and creative in addition to being empirical, which everybody already knew. All right. So I'm going to read this quote to you. This is from Stephen Dutch. He was a geology professor, I think, in a university in Wisconsin for a long time. And he said this in a article in the Journal of Geoscience Education. And look at the title of the paper. It's "The Standard Model for Reform in Science Education Does Not Work." Okay, what do you suppose the standard model involves? A lot of it is, hey, if you can teach the students like what science was really like, so the nature of science, then they wouldn't have so many hang-ups about certain subjects in science. So he's saying this doesn't work, and this is why he says it doesn't work. Students at this stage of development want certitude. If they do not get it from science, they will not respect science for its honesty, but rather will conclude that science has no authority. They will seek certitude from someone who does claim to have it, and there is no shortage of charlatans who claim to have it. So whatever else I have to say about this, let me just express that this is a legitimate concern, right? Start emphasizing the creative and tentative natures of science. Won't that turn some students off and make them think, oh, science isn't worth my time, I'll go and find certainty somewhere else? That's a real concern. But the problem is that when you come into the classroom with that kind of attitude, what you usually end up doing is, if you do mention that science is tentative or creative at all, you start waffling immediately because you're afraid of this, right? So it's tentative, but not that tentative, right? It's creative, but someone else would have come up with the same thing, if this person hadn't, and some stuff like that. So you can really waffle about this message, even if you do mention it at least. And so what you're doing is you're turning your bat into a weak little, I have a wheat sprout here. You hit somebody over the head with that, it's not going to do anything. Okay? So your students, I'm telling you, will go through the class if you take this approach, and even if you say it, they will not notice and engage with the fact that science has any tentative or creative aspects to it. All right. But I want to assure people who have that legitimate concern that I think the risk is not as great as you might think, that students are going to be turned off by learning how tentative and how creative science is. So here is a typical, very typical, most of the students said something like this when we tested out our program the first time. This was a class of elementary education and early childhood education majors, which are not known for being the students to get in class who are going to be most excited about learning science at a university, right? So anyway, they came in, a lot of these students came in with some baggage. So this student said, the concept that scientists come up with theories in order to help explain the universe and the world has made me more interested in science. The idea that scientific theory was concrete and absolute truth always irked me a little, but the concept that science is storytelling makes me more open-minded and more interested in knowing what scientists believe and how they explain the origins and workings of the world. And like I said, almost everybody said something along these lines when we asked the students, how the program affected their view of science, okay? Now, the people that I know, so I'd never met Albert Einstein or Peter Medawar or any of those people, right? But I have to say that the scientists that I personally know, that I most admire their scientific work, they don't just say to the students that science has a tentative and creative aspect. They lean into it, especially the creativity part. Okay, so here's an example. This is my friend Bill Casey. He recently retired from UC Davis in the chemistry and geology departments there. But he said something when I was talking to him once that I had to write down because it's so, I cracked me up because it's so true and so counterintuitive at the same time. So I thought it was funny. But he said, if I were competent to do it, I wouldn't be doing it. So think about that for a minute. What is he trying to get across? I think what he's trying to get across is that if you feel like you're completely competent to solve some problem, if you're a real scientist, you're bored, right, with that problem. There's so many exciting problems that nobody understands completely what's going on. Even if you can make some little incremental step in understanding the problems, that is a really intense experience. That kind of creative juice is important. In fact, one of the hardest things I ever have to do with graduate students in science is try to beat into their heads that it is okay to, when we're sitting in the office looking at some data, trying to come up with some credible sounding explanation for it, that it won't fall apart at first scrutiny. It's okay to throw out whatever stupid ideas they have. Because when you're in that creative mode, there is no such thing as a stupid idea. Okay, you just throw out ideas, start beating on them, and see what comes out stronger. Okay, if you are so worried about looking stupid or something like that, when you're in this creative mode, you will never have any good ideas because everyone has to go through a bunch of stupid ideas before they get to a really good idea. And putting yourself out there like that and exposing, yourself to possibly being shown that you're wrong or something like that, that goes against everything that a lot of students have learned all the way through school, right? You want to give the right answer. You don't want to look dumb in front of everybody giving the wrong answer. But there is no exact right answer when you're coming up with an explanation for something new. All right, so the next mine in the minefield that you have to contend with is, I call it no philosophy and a PhD. What do I mean? Well, PhD is an abbreviation for Doctorate of Philosophy, right? So you would think that if you get a PhD, you wouldn't just be good at doing science, but you could articulate a coherent philosophy of science, right? But this is from a paper by Joe Pitt, who was a philosophy of science professor. He says, it is generally the case that in no science or engineering curriculum are students required to take courses in the history, sociology, or philosophy of science, nor are they required to consider the relationships among the various sciences. Thus, the college science curriculum is merely more of the same the student was exposed to in high school. In other words, like I said, you can go all the way through to get a PhD and never even be exposed to more than a page or two in a textbook of anything like this. Okay? Now, I don't mean to be critical of people in that situation. That's just how the system has been set up. So all of us who went through science curriculum and got PhDs in science, we're mostly in the same boat, right? But just what we have to realize too is that just because we're good at doing science doesn't mean we're good at articulating, a coherent philosophy of science, right? Just like if you're in baseball, the best hitters are not necessarily the best batting coaches, because the best hitters are so talented, they don't have to even think about what they're doing that much, okay? So this, just to show you how bad it gets, okay? You might be thinking I'm making the problem bigger than it really is, okay? But check this out. Okay, so this is a couple quotations from an article by a biologist named Robert Sprackland. And he had this article in the American School Board Journal talking about basically how to teach about stuff like evolution and things like that. So in this first quote, he says, "In my 3 decades as a science teacher, I have met many university science majors who cannot properly define science." Okay, so he's acknowledging exactly the problem that I just articulated, right? Then later on in the article, he says, "Scientists make only one universal assumption in their work. Reality is real." Well, just think about that. Let it roll around in your brain a little bit, right? I mean, I also assume, and I assume all other scientists assume, that sunlight is solar. Like that's the same content there. It doesn't make any sense. And yes, scientists make other assumptions. What about the assumption that the physics that we can see now it can explain things that happened deep in the past, or on the other side of the universe? Or there's various things like that all scientists assume as part of their work, but they are assumptions. We can't go across the universe to see if we're right. We can't go deep in the past to see if we're right, okay? It's an assumption. So here we have an example of a scientist, PhD scientist, who recognized, PhD scientist who taught for 30 years by this point, who recognized the problem that the students coming up through the ranks can't articulate what science is, right, in any really coherent manner. But then at the same time, he's saying stuff like this, right? So I'm showing this to you not to put down this guy or anybody else. I'm saying that if you're sitting there thinking that, well, yeah, I can see how that would be the case for a lot of people, but not for me, maybe you take a beat and think about it. Could it be that you have some misconceptions, that because you haven't been forced to articulate much about the nature of science, and you have your ideas haven't undergone scrutiny by anybody but students who assume you know what you're talking about, right? Could this be the case? I'm hoping that some people will consider that a possibility. Okay, so now that brings us to our tool here, the Science as Storytelling tool. And before I get into what's in there, I want to assure people that the title aside, right, everything we say in here is just like a condensed version of a history and philosophy of science class 101, right? So if you picked up this book right here, it's a really actually small and good book, Samir Okasha's Philosophy of Science, a very short introduction. You wouldn't find anything in there that is foreign to what we're talking about in our much shorter article, okay? So we use this, basically how we typically use this is just to assign it as reading for the students, give them some kind of online quiz to make sure they did the reading before class, and then discuss it one class period. And aside from just referring back to the concepts throughout the semester, that's it, okay? One class period, that's what it takes. And like Brooks said at the beginning, he found out most of his problems with the students sort of melted away, right? Okay, so now that said, if we have this is about 20 small format pages, okay? It's not that much text. And if you're in the position where you have never taken all these history and philosophy of science classes, even though you're being asked to teach about the nature of science in your science classes, then you can use this text as well. Maybe you want to read more about it once you get into it, but you could use this text to make sure that you have sort of a coherent and proven sort of explanation of what science is all about, okay? And you can draw on the language to make sure you're saying it right. Now, I am one of those rare people who, I actually got a minor in philosophy, so I took some history and philosophy of science classes and things like that, okay? And I kept reading afterwards these kind of books. But even though that, you know, I'm ahead of the game in that respect, you can see the authors there are me and David Grandy. And Dave Grandy, he's retired from here now, but he was a philosophy of science professor here at BYU. And so I recruited him specifically to help me with this, like mostly so that he could make sure I didn't say anything stupid, okay? So even though I had some of that background, I was hesitant to go too, like, put my neck out too far. And I wanted to make sure a professional would agree with it, and he actually added several things to the discussion as well that were really useful. Okay, so I'm not asking you to get another degree in history and philosophy of science. Just read the article. If you feel inspired, keep reading stuff like this other book that I have shown here. But I'm trying to give you a tool as well as your students to correct some misconceptions and so on. Okay, so here's what we have in the presentation in this essay. We give sort of a definition of science, and it's a very loose definition, okay? There's actually shelves and shelves of books on what's called the demarcation problem. And the problem is, like, how do you define science so it includes all the stuff you want to call science and excludes all the stuff that you don't want to call science, right? So I'll write shelves of books on it, so we say up front, okay, this is kind of a loose definition. But science is the modern art of creating stories that could explain observations of the natural world and could be useful for controlling or predicting nature, okay? So people have always told stories to explain the world, but not all these stories are considered science, right? So for instance, why does this fiery ball go across the sky every day? Well, the Greeks said it was Apollo's chariot that he drove across the sky every day. Okay, does that explain the observation? Yes, it does. Would we want to call that science or equate it to modern science? Well, not really. I mean, most people would agree that's not exactly what we're talking about when we say science. What about astrology? Okay, a lot of people are into that. And do they make observations of nature? Yes, they do. Do they use it to explain and predict things? Yes, they do. Why isn't that science? Oh, well, we have to put some qualifiers on our loose definition. And that is that scientific stories, if we're going to call them scientific, they have to follow certain rules. And these rules are established for convenience in accomplishing scientific goals, okay? So these rules themselves are human creations. Could there be some other kind of science that somebody wants to do? Yeah, sure. But this is what we're talking about when we are discussing modern science in the modern world. This is how it operates, okay? That's what the rules are about. Now, if you have rules about what your stories can be like or can include and so on, the rules are both a powerful thing and a limiting thing. So obviously the rules are limiting, right? You can't do this, you can't do that. But they're also powerful. So if you limit yourself as far as excluding some things from how you operate in science, that would sort of muddy the waters and make it harder to do, then it can actually help you make progress, okay? But you have to keep in mind that these rules are human creations that are also limiting as well, okay? Now, the first rule that we give them is reproducibility. So scientific stories are crafted to explain observations, but the observations that are used as a basis for those stories must be reproducible, okay? So what are the limitations? What's the power here? Limitations is that you're sort of leaving out whole classes of observations, like, that are sort of personal experiences that nobody else witnessed, or internal experiences, so religious experiences that are personal, stuff like that, UFO abduction stories, that kind of thing. The fact is that people lie about stuff, they hallucinate, and or they just sort of thought they saw something and misinterpreted what was happening, right? This happens all the time. We all know it. And so is it a limitation to exclude stuff like that from science? Yes, it is, because there might be something that somebody claims that is actually true, right? But we're setting that kind of stuff aside just to simplify things. So hopefully we can not get caught in the weeds, right? Now, one example of this is meteorites. Okay, so meteorites are basically rocks that fall out of the sky and hit the earth. And people have known them forever as shooting stars, right? You can go out on some nights and watch these streaks of light go across the sky. Now, it's actually really, really rare for somebody to see that streak of light and watch it hit the ground, okay? So it's either you see the streak of light or you see some rock on the ground, right? So there's not this connection between falling out of the sky and sitting there on the ground, right? So usually when that would happen, in the rare occurrence, there was only like one person there or something to see it. But it turned out that in I believe it was the 18th century, there were a couple professors at Harvard who witnessed this happening. Streak of light, stone hits the ground, and they can go examine the stone, okay? Now, were they hallucinating? Well, probably not. People don't tend to have hallucinations that at the same time that are exactly the same, right? They'll see different things if they're both hallucinating at the same time. Could they be misinterpreting something? Well, sure. But again, both of them saw it. Could they both be lying? To manipulate people, get fame and glory, that kind of thing? I guess, right? The more people that are involved, the less likely that is. But still, somebody as smart as Thomas Jefferson heard about this. And the problem was that the idea of stones falling out of heaven was totally against what they thought they knew about how the heavens were composed. Okay? So whatever the prevailing ideas about what's up there were at the time, it didn't include a bunch of rocks that could fall out of the sky. And so Thomas Jefferson, one of the smartest people who probably ever lived, said, I could more easily believe that two Yankee professors would lie than that stones would fall from heaven. Okay? So it turned out that more people saw this kind of thing, okay? And so they collected evidence, and finally, they had to admit that, okay, this is real, okay? But I'm showing you this to illustrate the fact that, yes, it's a limitation, but it also, hopefully you can see how it clears some of the brush away sometimes so that we don't get caught in a loop because somebody lied or hallucinated or whatever, okay? All right. So one point I like to bring up with the students about this rule is that the observations upon which the story is based have to be reproducible. The story itself does not have to be reproducible. So for instance, some people will object to something like evolution because you can't go back in time to reproduce millions of years of evolution or whatever, okay? Which is true. But they'll go on and say, oh, see, it's not reproducible, therefore it's not science. But the story doesn't need to be reproducible. The story always goes beyond the observations that it is supposed to explain. If it didn't, it wouldn't be an explanation. It would just be sort of a catalog of observations, okay? Explanations have to go beyond the original observations. Now, another point I like to bring up with the students is that the inspiration for the story can come from anywhere. We don't care. I mean, in the end, you have to make a logical case based on the rules that we're talking about, right? But this creative process of coming up with a story to explain some stuff, nobody cares how that happened. So for instance, this guy, Auguste Kekulé, he was a famous 19th century organic chemist, and he came up with the structure of benzene. That's the thing there in the middle of the circle. So benzene is a molecule that's ring-shaped, and he was trying to use the ratio of different elements in it to explain how it was structured based on what they knew about how these hydrocarbon compounds bond. And so he came up with this ring shape, and that's what, to this day, everyone thinks that benzene looks like. Now, years later, long after he'd published this, he was giving sort of a biographical sketch of himself, and he revealed that one day when he was working on this problem, he had sort of this, like, he described it as a dream, but it was during the day and he was awake or something, and he saw an Ouroboros. An Ouroboros was an old alchemical symbol. That's this thing right here, the snake wrapped around and eating its own tail. And so that gave him the inspiration for thinking, oh, maybe benzene is a ring shape. So what, right? So just use that to illustrate, once again, that we are talking about a creative process here. And we can even use the rule of reproducibility to illustrate that. Okay, so rule 2 is predictive power. Scientists prefer stories that can predict things that were not included in the observations used to create those explanations in the first place. So the way we typically talk about it is that you're first, like, you have some observations and you try and explain them, right? And we call this explanation a hypothesis. And a lot of people think of a hypothesis as sort of just an initial guess about the answer, right? The explanation. But it's not just that. It's a hypothetical, right? And think about what a hypothetical situation is. It's where you think, well, what if this were true? What else would be the case, right? So we try and think through that story. The story always goes beyond the observations. And so we can say, well, if this explanation is true, what else would be true? And then we can look at those what else's and figure out if there are any of them that we could maybe test. And usually, I mean, always, there's more things than we could test with the equipment we have right now. There's always observations we wish we could make that we can't, right? But we see what we think we can do, and we start testing those. And when we have a story that seems to keep working mostly, right? And these tests pan out, we call it a theory. So it's passed a lot of these hypothetical tests that we made up. So do you see how a good scientific story is going to predict things? It's opening the way to testing. If you can predict things that you didn't already know, then you get more confidence that you're on the right track, right? Now, another couple points I have here is that no, a theory, this is in so many textbooks, right? But it's absolutely wrong. They'll tell the students that a theory, if you test it and test it and test it, eventually it graduates to become a law, a scientific law. That's not really what scientific laws are. Usually when scientists talk about laws, they're talking about concepts that sort of are generalizations of a bunch of observations. So for instance, this equation right there on the screen is Isaac Newton's universal law of gravitation. It's just explaining that it's just an equation that says basically the force of gravity between two objects is proportional to the masses of the two objects and inversely proportional to the distance between them squared. Okay? Just an equation. And it has no explanation for why massive objects would be attracted to each other. I mean, we can give it a name, gravity, but why? Why does gravity exist? And he had no answer for that. In fact, he was criticized by some of his contemporaries because they called gravity an occult force, right? There's no explanation for it. So, so you get the idea. That's what a law is. In fact, it wasn't until Einstein that anyone came up with a really credible explanation for why gravity exists. All right, so another point is that we don't know whether future observations will contradict the theory, so it always remains tentative. So remember this, a theory is the apex of science. That's the best we've got. It may be wrong, right? But we don't have, like if somebody dismisses a scientific theory because it's a theory, you need to tell them, the theories are sort of the best science has got, so like you're dismissing pretty much all of science if you dismiss something just because it's called a theory. All right. Next rule has to do with prospects for improvement. So I said scientific stories should be subject to an infinitely repeating process of evaluation meant to generate more and more useful stories. Useful for what? For making predictions and explaining things, right? Or controlling things. Now, this list of steps I have here is suspiciously similar to what you would see in any textbook about this is what the scientific method is, right? It's just not all there is to science, okay? So the idea is you make observations, you make up a story to explain the observations, you reason out some more consequences of the theory that go beyond what you already observed. You check those out, see if any of them pan out. And if they succeed, like so that the story passes the test, what do? Well, you're more confident that you're on the right track at least, right? You think you're probably closer to the truth than you were before. Even though we can never tell when we're all the way there. What if it fails? Well, if it fails, the test, we know that something is wrong. What is that something? We don't know. It could be a lot of things. It could be the test. We made some assumptions and figure out that this is a test of our theory that like those sort of auxiliary assumptions were not exactly right. So we can adjust some of those, right, and maybe make it work. Okay. We could have done something wrong in our test, like the instrument could have been on the fritz or anything like that. Or the whole thing could be garbage, okay? So our options are we can discard and replace that theory with a new theory or a hypothesis or whatever that explains more observations better, okay? And we can go through this process again. Or we can take the existing hypothesis or theory and modify it, right? Tinker with it so that the story is a little more complex, explains more things, and covers more of the bases, that kind of thing. Or this is one that doesn't get talked about ever in the textbooks, is that you can ignore it for a while, right? There's all kinds, like every scientific theory has a certain set of observations that the scientists working on that think are relevant. But there are an infinite number of observations that could be made that we just don't think are relevant, so we don't make them, right? Or we don't connect those observations to this particular theory. So if we get in a situation where we don't quite know what's going wrong, even though we failed some of the tests, we can say, well, this is a theory works pretty well, and so we're going to keep it for a while, and let's keep this on the shelf and revisit this from time to time to see if we can come up with something better. Okay? That is an absolutely legitimate thing to do. All right, so now we come to another mine. So we're sort of halfway through our explanation of the science's storytelling rules, I guess. But the next one intersects with religion a little bit. And here's a quote from this article by Paul Farber, another biologist, who wrote an article about teaching evolution in the American Biology Teacher. And he said, what about religion? Religion resides under the surface in any discussion of evolution. So, and again, this goes for a number of other scientific subjects that you could be teaching about as well, like the Big Bang or whatever, okay? So what he's trying to say is that even if like you don't want to bring in religion to your science class, it doesn't matter, because whether you bring it up or not, some of your students are thinking about it the whole time, okay? So if you want to reach those students, you need to say something about it, right? That's what he was advocating. All right, but here's the problem gets deeper. It's like, you know, I talk about how scientists, even if they have got a whole PhD in science, that doesn't mean they took any classes ever about history and philosophy of science so that they could have a good idea of how to articulate a coherent philosophy of science, okay? But it's the same when religion comes in. A lot of scientists and science teachers don't want to bring in religion into their class because they feel uncomfortable about it because they aren't religious themselves. So here's some data from this paper that I have here, Religion Among Academic Scientists, Distinctions, Disciplines, and Demographics. So in this article, they did a lot of polling of scientists and comparing that to the same polls of the general population and so on. And one conclusion they came to was that, on average, scientists aren't as religious as the general population. Doesn't mean there's no religious scientists. It just means, on average, it's less. Okay. So, for instance, in the general population in 2007, when this paper was done, 90% of the people in the USA polled said that they believed in God. They did the same poll with scientists at what they were calling elite universities, okay? So maybe it's a little bit different for scientists in general or something, but this is instructive still. It was only 35 to 40%, okay? So again, there's a lot of scientists out there and science teachers who, like, they're not religious, they don't want to talk about this, they just want to talk about science. And so they might just ignore it. Instead of engaging with those students who are worried about it. Okay, now what if the scientists are religious? Well, religious scientists tend not to go to the same churches as the general population or who they can expect in their class, right? So for instance, at the time, in the general population, 13.6% of people identified themselves as evangelical or fundamentalist Christians, okay? But at those scientists at the elite universities, it was 1.5%. That's a factor of something like 9, right? Difference. That's huge. Now, they did other ones that I don't have up here. Like, for instance, they looked at Catholics, and they had people classify themselves as traditional Catholics, moderate Catholics, or liberal Catholics, right? And so they would, in the general population, it was roughly equal proportions of each. But among the Catholic elite scientists, it was the traditional Catholics were vastly outnumbered by the liberal Catholics, again, by their own description, okay? So even if you go to the same church as some of your students, that doesn't mean that you think about religion and how science relates to religion or anything the same as those students, okay? Let alone if you're teaching at a state university and you get just like everybody in there, right? I'm teaching at a place at BYU here that is probably one of the most religiously homogenous universities, major universities in the United States, okay? And yet, even in my classes, there's enough diversity that I can get into trouble if I start assuming everyone thinks the same way about these kinds of issues. Here's the last thing. Religiosity in the home as a child is the most important prediction of present religiosity among this group of scientists. So, in other words, for the most part, the scientists aren't growing up in religious homes and going to college and then losing their faith and becoming atheists or something like that, right? Mostly what happens is that non-religious people are self-selecting into scientific disciplines, okay? Because why? I don't know, maybe that's how they make some sense of life, okay? So think about this for a second. We kind of have to talk about religion, but a lot of these scientists that are expected to do that, address it somehow, right, are in no position to talk about any of it. They didn't even grow up in a religious home. And if they did grow up in a religious home, how many kids do you know that age that have a really sophisticated view of even their own religion and how different people in their own religion, differ in their views, okay? So we have a lot of science teachers who have very unsophisticated views about religious thought because they don't have that much experience with it, okay? So we're going back here to that book, Teaching About Evolution and the Nature of Science, okay? And from the National Academy of Sciences. And I'm going to have 3 quotes from here, okay, from this book. So this committee of scientists got together and they said, we're going to tell you how to not just teach evolution and the nature of science, but we're going to tell you how to talk to students who have religious hangups about evolution, right? And so what are we going to say? Well, here's one thing. They said, well, aren't scientific beliefs based on faith as well? Usually faith refers to beliefs that are accepted without empirical evidence. Now, I know people who would describe it exactly that way, okay, that are religious in some way. But most of the religious people I know would be insulted by that, right? Do we think of faith as something that we just believe without any evidence whatsoever? No, we think of it as something we believe with incomplete evidence, which, once again, because science is tentative, isn't all that different. Maybe there's qualitative differences and in what counts as evidence and so on and so forth, right? But in principle, it's not any different than science, right? If science is really tentative, which these guys are teaching, okay? Next quote. Most religions of the world do not have any direct conflict with the idea of evolution. Now, imagine you have a fundamentalist Christian kid in your class, and you say that. How are they going to interpret it? They're going to interpret it as, well, I'm pretty sure that every pastor I've ever had says that we do have a conflict with this stuff, and so, therefore, you must be telling me that I need to switch religions, like you're a missionary for the Unitarians or something, okay? So do you see how that would be read far different than like what you mean when you say that? Like most of the people I know that would say stuff like this, they don't want to alienate their students, not at all. Okay, so last one. At the root of the apparent conflict between some religions and evolution is a misunderstanding of the critical difference between religious and scientific ways of knowing. Religions and science answer different questions about the world. Whether there is a purpose to the universe or a purpose for human existence are not questions for science. So let's pick this apart here. Number one, there aren't any conflicts between science and religion, these people are saying. They're saying that they're only apparent conflicts. And what if you think you have a conflict between your religion and evolution or whatever? You're wrong. What the problem is that you don't understand your own religion. If you did, you would know that religion only answers questions about the meaning of things and morals and so on and so forth, right? It doesn't answer any questions about things that happen in the physical world, okay? Now, what if your religion doesn't fit that bill? And I can tell you that there are a lot of people whose religion does not fit that bill. Once again, you'll be interpreted as saying that there's something wrong with their religion and they should change to one of these other religions that teach something like that's more compatible with science, okay? Now, but just think about this. You could say all this stuff and a lot of the students would respond positively to it. They aren't that religious. Maybe they grew up religious, but they never took it all that seriously, and they're 18 and they're in your class, and so, okay, they'll just believe what you say, or they're not going to get up in arms about it at least. But there will be some students in the class who will be deeply offended by you, by this. So is there some way to go about this that doesn't set off all these minds for some of your students? All right, so when we talk about the next rule, we're addressing this very directly. So the rule is naturalism. In other words, scientific explanations do not appeal to the supernatural. Only naturalistic explanations are allowed. So only natural causes for things, no supernatural causes. And when I'm talking about natural versus supernatural, I'm talking about things that happen according to regular laws of physics and so on, even we don't completely understand those laws, but it's a regular thing, right? Versus some entity poking their finger in and making the rules change temporarily for a while. That's what I would call supernatural, okay? So we give them some practical reasons why scientists, even if they're one of the religious ones, even if they're one of the sort of more conservative, miracle-believing type of scientists, right? Even those people will set aside the possibility of supernatural causes when they are doing science. Why would they do that? Well, there's practical reasons. Stories that employ supernatural causes usually don't result in precise predictions of future observations. Okay, so that makes it kind of hard to test. So for instance, Apollo's chariot going across the sky, what are we supposed to look for? Are we supposed to look for giant horse droppings or something, right? But if we don't find them, what if the celestial horses are different than earthly horses, and so we shouldn't be expecting that? It's hard to say, right? So that's the kind of thing I mean. Next reason, it's hard to put limits on supernatural causes, okay? So like if it could be Apollo's chariot, it could be Odin's shiny helmet, it could be any number of things from any number of religious viewpoints and so on, okay? It's hard to like say, oh, it has to be this one, but not that one, if they're not producing very precise predictions, okay? I'm not trying to say this is universally the case either. I'm just saying that a lot of supernatural stuff sort of fits more in this category, and so we're doing some simplifying here once again to limit ourselves, but also make the process more powerful for certain purposes, okay? Next point we bring up is that we want science to be an activity that people of any faith or none can continue or can contribute to, okay? So the question is, do we really want like Hindu science and Confucian science and Taoist science and Christian science and this other kind of Christian science and whatever, right? Do we want to balkanize it this way, or do we want this to be sort of an activity that we can set aside a few things that are dear to us for the moment, so that we can talk about making useful, making stories that we can use to make useful predictions of things that happen in the world. Okay. And then the last one, attributing everything to the supernatural is a great way to miss opportunities to create useful naturalistic explanations. So the poster boy for that, point is Hippocrates. So I think he's like 4th and 5th century BC Greek physician. And he's so famous that even now doctors take the Hippocratic Oath, right? You've heard of that? Anyway, that's because of this guy. And he revolutionized medicine. Why? Because the way medicine was practiced in his day, at least in Greece, was that people assumed that if you got sick, it was because some god or other was mad at you. And so therefore, most of the treatment was, burning some incense and, pray, have some priests praying over you and so on to try and appease the gods. And that was, make them comfortable, but that was mostly it, okay? And so his idea was that he didn't come in and say, those gods are bunk, right? He said that, well, what if some of those illnesses are, they have natural causes, and it's something we could figure out, and we could do something to like explain it and use that explanation to come up with treatments for it. And so that's what he did. He was very systematic about how he did it. And he revolutionized medicine. Now, even nowadays, very religious people might still believe in the power of prayer and so on to when they're sick, and they will do all that kind of stuff, and yet they'll still go to the hospital if they're really sick, right? Or go to the doctor. That's the idea here, is that if we're too lazy to look for naturalistic causes for some things, we might be missing out on an opportunity to have something that's very useful. Okay, now I have something here. An important point that we bring up explicitly to the students is that if there are two systems of thought, like a particular religion and science, for instance, where one system of thought says supernatural causes are A-okay, and the other one says, well, no, we're completely ruling those out for the purpose of doing what we're doing, okay? If that's the case, then there will be some genuine conflicts here and there. It doesn't mean everything conflicts. I mean, lots of religious people believe there are supernatural causes out there, but most of the time the world operates in a regular manner, right? So there's going to be genuine conflicts. Okay, but you have to be careful how you talk about this, because when you say certain words, people take it to mean different things. So this guy right here is Russell Nelson. He's the president and prophet of the Latter-day Saint Church here that runs this school. And a lot of people don't know, he's like 100 years old now and still going strong, but for a long time he was a very famous heart surgeon, okay? So this is what he said: there's no conflict between science and religion. Wow, that seems like it's directly contradicting what I just said, right? But then he goes on, conflict only arises from an incomplete knowledge of either science or religion, okay? So what he's basically saying is that, yes, science and religion, as they exist now, with incomplete information, are going to conflict sometimes, but in the end, it's all going to work out, okay? But people pick up on language like this when scientists, especially scientists who are religious but sort of in a different way than some of their students, start saying stuff like that. There's no conflict between science and religion. Remember, a lot of students are going to interpret that to mean that that you mean there's something wrong with their religion and they should join some other religion. All right, so how do the students take this? So again, we tested this here at BYU, and it's actually been tested in several state universities as well. But here's one of a very typical student comment. This person said, it used to bother me that religion was left out of science, but now I see that it makes good sense, as all curiosity might be lost if we chalk it up all up to things we think we cannot understand. Plus, I think there's always the danger that we would that the wrong supernatural explanations would prevail. Okay, so this is directly referring to a couple of the different explanations that we gave in the essay. But this was a very typical response. Even the students who said, well, I think they should allow the supernatural in science, those same students would say, but I can see why they do it, right? And so the upshot is that they or the result of this was that the students almost uniformly came out thinking better of science, thinking that the scientists aren't out to attack them or their faith, so they can relax and listen and consider evidence and so on. Okay, next rule is uniformitarianism. Basically, an extension of naturalism to some extent at least, but the idea is that we assume that past events can be explained in terms of the natural laws that sort of apply today, right? There wasn't completely different physics and chemistry going on 500 million years ago, okay? Do we know that? No, we can't go back in time to test that. But, you know, we can assume it and see how much traction we can get making that assumption. Next rule, simplicity. Scientists assume that nature is simple enough for human minds to understand. Now, think about nature as in the universe, and think how small your brain is compared to the universe. Is it really reasonable to think that humans have enough brain power to understand the whole thing? Probably not, but we have to make this assumption, because if you assume you can't understand a problem, then you won't try to solve it, right? So it's just the cost of doing business. But one thing we bring up to the students is that this does not mean that scientific stories have to adhere to what we call common sense. Now remember Newton's law of universal law of gravitation, which was just an equation, no explanation. Well, Einstein here came up with an explanation for why the gravity exists. And it has to do, I'm not going to explain it all here, but it has to do with warped space-time. Motion of bodies around warped space-time. What the heck is that? Could you go down the street and pick some random person and have them explain what is meant by that? That would be pretty rare to find somebody, right? That could do that. So what we find is that the deeper we can go into science, at least when we're talking about fundamental things, like things that are really small or really big, we find some really weird stuff that's beyond our experience, okay? So it's not exactly common sense. Okay, last rule is harmony. The scientific explanation should not contradict other established scientific explanations unless absolutely necessary. So the idea is we're trying to create one big story that explains all kinds of things, right? And it can't have contradictory elements. That would make it a bad story, right? Are there contradictory elements right now in this big story? Yes, there are. And when we notice those, we can go and try and see what the problem is. That's a flag that goes up that says, hey, scientists, you should go look at this some more, okay? So we're holding out the possibility that what we have now could be wrong in various ways and it'll need to be adjusted or changed. Okay, last point about it is that science, it really has to be a community endeavor. Like people have in mind when they think of scientists, this lone genius in some windowless basement, right? Coming up with these really grand ideas and so on. And they get mad at you if you start telling them, well, most of whatever kind of science, or the vast majority of them say that they think this is what's the case, or that's what the case. They'll get mad at you. Science isn't about consensus, but actually it kind of is, because a big part of science is exposing your ideas to criticism by other experts, okay? So you know, if there's an overwhelming consensus about something, does it have to be correct? No. But if you want to go against that, the responsible thing to do is to learn all you can about it so that you're competent to make arguments against the consensus view, not just dismiss the consensus conclusion because you can find some expert over here or over there who's sort of on the fringes and disagrees with some of the consensus, okay? This happens all the time in public discourse, but people don't understand that some scientists are nuts, right? Some of them aren't as smart as others, right? So And some of them are super geniuses that are really on the right track and everyone else is wrong. And it's really hard to tell which is which at any given point in time, okay? So when in the public sphere, people are bringing up the consensus of experts, that is not anti-science. It goes right along with the way science actually works. Okay, just to rehash what some of our key strategies are in delivering this. Number one, the word storytelling is our bet to let them know that what they're hearing is not the same thing they learned in junior high. So they should listen up and figure out what's different. Okay, we note exceptions to a lot of the rules that we give, right? And not just exceptions in principle, exceptions in history of science. So there's things that everyone wants to call science, but it was a little different in this case than what we usually, the rules we usually impose on science. So we'll bring stuff like that up. We talk about how the rules can limit science, but also empower it in different ways, okay? And we ask students to think for themselves about whether particular rules are a good idea. Like, for instance, we asked the students about, what do you think about this naturalism rule? Do you think it's a good idea or bad idea? Most of them came to the conclusion that it was a good idea. And some of them came to the conclusion that, I probably don't agree with that idea, but I can see why they do it. So, you know, they feel better about it still. And then last, we point out the inevitability of occasional science-religion conflicts. This is not to say that science and religion are always at war or anything like that. That's not the case. And that hasn't been the case if you look into any history of how science has related to religion. It's complicated, okay? But if we don't say that, if you're assuming this over here and you're assuming this over here, sometimes you're going to have some conflicts, then they take away just some pablum about how science and religion don't conflict, right? Or they shouldn't conflict, or like whatever. Yes, they should sometimes, okay? Because of how we practice science and how, like, at least some different religions think about it, okay? And for the most part, when you tell them that, they can say, oh, okay, I see why there would be some occasional conflicts, and so I can chill out about it. Okay, so here's another example of a student response. The explanation of science and storytelling has helped me see that theories don't have to be and aren't necessarily considered to be absolute total truth. It just means scientists have observed things in our world and are trying to explain it considering the rules of science. I'm more willing now to think about theories instead of just immediately rejecting them. I don't feel so threatened by theories now because they don't have to be absolute truth. In other words, this is like a big pressure valve, right? To release the pressure on these particular types of students who are really having a hard time with this, to say, look, we're not trying to shove this down your throat. We're acknowledging that all this stuff could turn out to be false, and we could come up with a better explanation of more data tomorrow, right? But if you can look at it that way, you can just relax and talk about the evidence, right? Well, how much support does this idea have? Okay, think about, are there other ways to think about it? Like, how believable are those other explanations? All that stuff, okay? Now, one of my last things here is this teacher. This was Ann Bykirk-Kaufman, who is a geology professor at Cal State Chico. Okay, so this was, like, I don't know, almost 20 years ago. I gave a talk about this at a GSA conference, and she was there. She asked for the essay, and I gave the version we had then to her. But the backstory, which I found out later, was that she had been teaching a Geology 101 type of class, okay? And she had always felt bad about not having a unit about evolutionary theory in it. She felt like she was neglecting her duty to help the students understand what's going on there. So she decided she was going to do it. She came up with this disarming preamble about, trying to relax people about the science and religion thing. And then, was talking about science and religion not having to conflict, blah, blah, blah. And used some material from this Understanding Evolution website at UC Berkeley. And she thought she did a great job, just hit it out of the park. But then she got her student reviews back and she was ripped a new one, right? The students were saying she was rude and sarcastic. And if you met this person, like, those are not the vibes she gives off, right? Seems very nice and caring and concerned if you meet her in person. But look at what she said about her experience after she got the essay. And she didn't even make the students read them. She just used it as a sort of, these ideas as a sort of preamble to what she was going to say about evolution. And the experience was the exact opposite. The students were saying, oh, I never understood evolutionary theory before. Now it makes sense. They were saying how much they appreciated the way she approached this. So this is just to remind you that there are some real minefields out there for some of your students. And if you want to navigate around those and not alienate them, you can. There's a way to do it. And in that like, notice what I didn't say in this presentation when we were, for instance, talking about religion, right? What I didn't say was what religion is. All I said about it was that, a lot of religions are okay with supernatural causes. And if that's the case, then, okay, you're going to have some conflicts from time to time. It's inevitable, right? That's all I said. I didn't tell them what religion they should believe in. One of these other religions that doesn't have a problem with science, right? I didn't tell them anything about what they should believe or trying to define what they do believe, even though I don't know that, okay? We're taking a different tactic on it and avoiding that. We're addressing the issue without hitting these mines, is what I'm saying. Okay, so now if you want to learn more about it, we did 2 papers in the Journal of Geoscience Education about this. The first one is sort of commentary on like what we think is going wrong with people trying to teach the nature of science and the science-religion interface. And the other one was basically tests, a test of our concept right there with some students in a class, okay? And like I said, other people have tested it at like state universities and something, and so on. And so this is not just something that we can use at religious universities that can't be used other places. It works just as well anywhere you do it. So thank you for your attention. And I'll open up to questions if you would like to ask any. And also, sorry it took so long. So dealing with conspiracy theories. So that would be a class of baggage, right? But if you talk to much, and what you're from Roosevelt, right, Riley? So I know you talk to people who believe in conspiracy theories. But now, so if you talk to those people, what I've noticed is that they tend to be, their view of science is like I described. It's good science versus junk science, right? So they have this black and white view of it that is not realistic. And like, how do you pry that out of their hands, I guess? I don't know, but it won't happen unless you have you can have a sit down with them and talk about what science is really like. And coming from you, who's a working scientist, that might hold some weight for them. That's all I can tell you about it, I guess. But that's a particularly nasty form of baggage, right? Anybody else? Yep. Yeah. Well, yeah, students check out, but why did they check out? Do they check out because they have ADHD or because, they have rotten things going on at home or what? There's all kinds of reasons. So you don't know, and sometimes you can't know what's going on. So that's why we tried to design this so that it would sort of end the arms race or have people set down their weapons for a lot of different, when they have a lot of different kinds of baggage, right? And sort of try and realize they can see this in a new way that's actually more exciting than what they thought. Does that answer your question? Yeah. Well, if you're a college teacher like me, you get student evaluations, and they'll say stuff if they didn't like what you said, if they felt insulted by it, and so on. You'll get some feedback then, but that's after the semester's ended, right? And so you want to try and do something at least that anticipates a lot of possible different problems, right? Anything else? All right, well, there's refreshments out there for everybody, and thank you for coming.